This lesson is on section 4.1, which is on factors and prime factorization. The first thing we need to do is review some vocabulary that we'll see in this chapter and section. So the first is a prime number, which is a whole number greater than 1 that has exactly two whole number factors, 1 in itself. Hopefully you're familiar with prime numbers, but examples of these include 2, because the only way to get 2 is 1 times 2, so the number itself and 1, or here, 1 in itself, you can see. 3 is another example, 5, 7, 11, etc. A composite number is different because this is a whole number greater than 1 that has two whole number factors. More than two whole numbers, so more than 1 in itself. It has another one. So for example, 4 includes 1, 2, and 4 because you can get 4 by saying 2 times 2. So it breaks down. Another example is 6, which is 1, 2 can also go into it, 3, or 6. So these all have more than two whole number factors. Prime factorization is when you write a number as a product of prime numbers. So for example, instead of saying 6, we would say 2 times 3 because 2 and 3 are both prime numbers. Or instead of saying 10, you could say 2 times 5. So you're writing it out as a multiplication of only using prime numbers. In a factor tree we'll go over, but that's a diagram used to find this prime factorization of a number. So you may remember you may have 10, this is a simple one, 2 times 5. It helps you figure it out, but when you have much larger numbers, this is very helpful. And lastly, a monomial is a number variable or the product of a number and one or more variables raised to whole number powers. So you'll see this later, we'll go through it, but say you had 45 x squared, you can rewrite this as 45 broken down into prime numbers only, so 3 times 3 times 5 times x, because we know x squared is the same thing as x times x, so breaking it down. So that's what a monomial is showing. But let's go through some example problems. So the first example problem is, say you're at a party and there's 30 people at the party and you want to play a game. In order to play the game though, you need everyone to be divided into equal sized groups. But you have to have more than one person in the group, and you can't have more than 10 or the game isn't going to work. But what I want to know is how many different group sizes are possible. So 30 people total, you need to be divided into groups. The first step is you want to write 30 as a product of two whole numbers in all the possible ways. So for example, you could get 30 by saying 1 times 30, 2 times 15, 3 times 10, or 5 times 6. All of those are going to give you 30. The second step is then to use the factors to find all the possible group sizes with more than one person, but no more than 10. So for example, 1 times 30, that wouldn't work because the group size is 1. Or here, 2 times 15, you couldn't have 2 groups of 15, but you could have 15 groups of 2. So for example, here you could write them out, so you could have 3 groups of 10, or 10 groups of 3. You could have 5 groups of 6, or 6 groups of 5, or 15 groups of 2. But you can't have 2 groups of 15 because that would be greater than 10. So the answer would be there's 5 possible group sizes. What I'd like you to do is some practice problems. You don't have to use this party situation, but I just want you to write down all the factors of each of these numbers. So like what we did in step 1 here. So for 42, write out all the possible ways you can multiply two numbers together to get this, get 42. So press pause now and try that. The second example is, let's get into how to do a prime factorization, and we're going to use a factor tree for this. So say we want to find it for 540. We'll do two examples to show that you can do this in more than one way. But the first thing we do is, at the top of the tree is always the original number. And then after that, you break it down into two factors. It doesn't matter which factor you pick, as long as you keep it neat and consistent. So for example, if I wanted to say 10 times 54, that's going to equal 540. But we need to break it down until we only have prime numbers, and neither of these are prime numbers. So then let's focus on the 10. How can we break this down? Well, we can say 2 times 5. And it's always multiplication. Be careful not to add. And these are two prime numbers, so that's great. That's not going to get simplified anymore. 54 we can break down into 6 times 9. And there we go. But we're still not simplified because 6 and 9 are not prime numbers. So the next step, we bring down any prime numbers, and we continue to break down anything that is not. So here, 6 is the same thing as 2 times 3, and 9 is 3 times 3. So now we have a factor tree. So what we can do is, all these numbers are prime here at the bottom, so this will become our prime factorization. And we write this as, there's two 2's, so it's 2 squared times, and you increase the number, 3 cubed, because there's 3 3's, times 5, and 540 is equal to this. Now let me show you that this works even if you do it a different way. So instead of doing 540 is equal to 10 times 54 as our first step, we could have said 20 times 27. Or any other set, but we'll do this as a second example. 20 can be further broken down into 4 times 5. But again, if you could have done 2 times 10 as well. So there's lots of options here. And 27 can be broken down into 3 times 9. We have two prime numbers here, but 4 can still be broken down into 2 times 2. And 5 can come right down because it's already prime. 3 can come down because it's already prime. And 9 can be broken into 3 and 3. So again, we end up getting the same result at the bottom. We still have 2 squared, 3 cubed times 5. So what I'd like you to try now is, 1, tell me whether each of these numbers is prime or composite. And if it is composite, write its prime factorization. So complete a tree to show me that what it is when you break it down just into those prime numbers. So press pause now and give it a try. The last example is, remember that monomial term. So we're going to factor a monomial. So this is going to include variables usually. But the first step is just like the tree we did in the previous. So if we start with this 54 and we break it down into prime numbers by using a tree, we can get 2 times 3 times 3 times 3. And then this x times x times x, since there's 3 x's, and y times y because there's 2 y's. So this would be factoring a monomial. And in this case, you'll see we get rid of those exponents. So instead of writing it as 2 times 3 cubed, we're getting rid of that. So monomial, meaning there's only one of each. There's no exponents here. So what I'd like you to do is try the following. Hopefully you can read it and it's clear enough, but factor these monomials. So try each of these on your own and bring them with class to you tomorrow. That's all for this lesson.